So here it is the question given is we have to generate all of the parentheses here. We is given the n is equal to 3, and so we have to generate all of the whatever the combinations of this valid parentheses. We have to generate these functions. Like let's say this is for n is equal to 3. So n is equal to 3 means there is a parenthesis which is of length 6, because it is since it is 3 for this, 3 for this, so this is a valid. Again we have to see for this is also valid, this is also valid. So basically all of the possible combinations we have to generate all of these. And now what is the brute force? First of all, whenever in this question, whenever any of the question, if it was asked if let's say we have to generate all of the combinations or all of the permutations or any kind of data stuff, so the very name approach is this is used, we have used recursion, or we can say like recursion, or is another name is backtracking. So there's a very brute force here. So like how we do this. So I'm go for this. Okay, so now let's say I've given here that n is equal to 3 here. Okay, so n is second, let's write is as we have given n is equal to 3. So what it means, we have to generate all of the first of all, what is the what is the recursive, we make a recursive tree here. Initially we have our empty array, and our initially our n is equal to 3. So up to how we have to generate this, we have to generate this up to our length is become 6. Means first of all, what is the operation here, what I have what are the options I have. Initially on, let's say on the left side I insert opening bracket, and on the right side I inserted closing bracket. So now it becomes one opening, and now it become one closing. Now further we expanded. Now here we have expand one opening here, and here we insert one closing here. Again also for this, here we have also two options there. Here we insert opening there, and here we insert a closing there. Now again we inserted there's a opening there, and here we insert closing there. Okay, so like this trees is goes on until its length is become 2n, or we can say until its length become 6. Now let's say if it is goes on to till length so it is goes of 2n depth here. And whenever we have to like this is comparatively very easily, we have to generally talk about the skew tree. Okay, so like let's forget it. So this recursive, we had not need to dry run all of this. So whenever its length become 2n, or we can say whenever its length become 6, we have to check what are the valid cases here. And we know very well like how to check any parenthesis as a valid. First of all, like we can also use a stack here. Like I can you can see in my previous videos, I also already taught it how to check a parenthesis as a valid or not by using a stack. And also if we have to like skip this extra space for a stack, we also use the like simply count variable, and simply if it's opening we simply increment our count, and if it's found closing, so we decrement our count respectively, and check if it's our resultant is 0 or not. So it so basically this is my brute force. What it means, we simply generate all of the we generate all of the parentheses, and now at the final step we simply check if it's valid, so we insert it some in our answer, otherwise skip it. So like go for our brute force. So see, this is our brute force here. So like here our main function here, first of all I pass the n function, n value, and initialize n, and pass in n, and like this is for the initialization of the final answer. It contains a vector of string, and like I have to simply make a temporary string there, which is I renamed as s. Okay, I call solve function, and after calling solve function I simply print my whole answer here. So okay, so now let's check for the how I write this valid solve function. So I pass the I define the solve function here, where I pass solve s, the s string there, the whole our answer vector here, and the size of it, this and here. So first of all, what is the base case? Base case is whenever the our string size becomes a 2n, means we have to reach of the final stage, and now we see if it is valid, so we push in our answer. Otherwise, so in both cases we skip this, and since we have reached this, so we simply return from this. And now we simply do our a very traditional template of a recursive function. So how we do this? Initially, first we insert the opening bracket here, we solve for this, and now after this we pop out this. Similarly, we insert our closing bracket, we solve for this, and we again pop out this. Okay. And how we do how we define the valid function. So I'm don't go for the stack method here, because that takes off an extra space there. So I simply write how we do it. I simply initialize a count vector, and I've traversed whole of the string here, and if I found opening bracket there, I simply increment the count, and in the else condition I decrement the count. One of the most crucial thing that that save us the very most steps in there, if any of the condition, if any of the index, if I found my count becomes less than 0, so what it means? So let's explain it by this. So okay, so see this, let's say our string is become here, let's say this is a opening there, there's opening there, there's opening there. Okay, so there is a closing there. First of all, let's say this is a string there. So initially your count become 1, count become 2, count become 3. Now since I found this, so count become 2. Okay, now count become 1, now count become 0. If I again using the closing bracket, so if count become negative, so what it means? So if any index if I found the count become less than negative, so it is guaranteed that it can't be become valid again, because it doesn't depend on how many of the opening bracket we are use here. If I make its closing bracket greater than our opening bracket, so it become invalid. So that's why I use the extra condition here to avoid many of the useless step here, that if any condition, if a count less than 0, it means it doesn't able to become the valid again, so it means simply return false condition. And in the final check we see, so if count becomes 0, let's say if there is a case here, you can use this. Okay, there's a case, there's a count become 1, then 2, then 3, then 2, then 1, but the final resultant is not at 0. So what it means? If count is positive, so what it means opening bracket is greater than closing, so it is not valid. So that's why we return this in the false condition. Otherwise, if it is 0, means all are balanced, all are simply balancing each other, so that's why resultant count is equal to 0, so return true. So this is the very brute force here. But see for this time complexity. First of all, what's the time complexity given in the question? There's n is equal to it, so very very small constraint here. So what it mean? First of all, during generating the all of the substring here, okay, as I'm talking about this, if we have to talking about the each position of the string, so what are the possible options here? Let's say if I'm talking about this, if I'm talking about any of the indexes, what are the possible options for this? Either there can be opening bracket there, or either there can be closing bracket there. Okay, so it means two options there, and there's a how many of the positions is there. Since n is equal to 3 given in the question, and basically here our size become 2n. Okay, so it is given in the question. So what it means, for each step we have two options there. So total of the options for the all of the operation, so it becomes simply 2 power 2n. Okay, so you recite this, so I think you understand it. For each of the places we have the two option, and how many places there? 2n, so that's simply 2 power 2n there. So this is the simply time complexity. And since if we have to reach for the final condition, we have at each operation we also see whether it is valid or not. And so how we check valid condition? So for valid condition we have to simply traverse all of the length of this final string there. So that takes also 2 power n 2n also, so that takes 2n also. So the total time complexity is become 2 power 2n into 2n. So this is the total time complexity. And since if we have to say the space complexity, so it's simply a recursive space. So how many so how we define the space complexity of this, like this recursive tree? So it's simply the depth of this recursive tree, and till how goes on. So it goes till 2 to n, because it's the we start from the empty array, empty string there, and we go till this string size become the 2n. So simply its depth is 2n. So this is the space complexity, this is the time complexity. Okay, this is the brute force. Now, like how we optimize this, or can is it possible to optimize this? So yeah, uh, here what we do, like if we have to check what we do wrong here, we simply generating all of the subarrays even if it is not valid, till also since also we generate it. So we can optimize this by using making, or we can say generating only valid parentheses, or we can say only valid string there. So if any of the condition, like let's say for this condition, if I see it is not valid, we simply don't have to go for the till the n of 2n size there, or we simply for this condition here it is not, again not possible, so there's not need to go for this. So that's why we simply check for the each of the condition. So now how to do it? So like it is not possible, we have to generate for each, if it for each step, if we have to check valid, we have to check valid, so that takes off an average. So this is again not optimize it. So how we do it? So there is a one conceptual thing here. uh, let's say we have to expand this return. Okay, we see one thing here, any valid parenthesis, what it consists of? It simply consists of, one is opening bracket, there's again is other is closing bracket there. Okay, so like how we do it this? So let's say if I have a string there, so okay, this is my string there, let's say I have to return it as, so there's a s is a string there, and there's initially our string is empty. So what are the two operations for this? So there's a two operation is either insert opening or either insert closing. But if I have to insert closing there, so it become invalid. Yeah, because so first of all, what we see here, for valid condition, I can say for the valid condition, it is necessary that closing must be less than equal to opening. Yeah, if our closing is greater than equal to opening, it at any condition we simply return it become invalid. So if we initially write the closing bracket here, so closing become greater than opening, so this condition is not fulfilled. So there's the only option is that it simply become as we simply insert opening here. Okay, so the other condition is not possible here. Okay, now if we have to also expand this into two part, like this is expand to two part, and since there is no condition here, so what is the operation here? We simply insert, there's a opening, opening there. Okay, and what is in this case, here is we insert closing bracket here. So I have to expand for this condition. There's either we expand, so like how to do it, either we expand opening bracket, or in the lower part we can expand the closing bracket. So now it is also valid, so okay, so don't worry. So means these are valid steps there. Okay, again it can be expand in two conditions. So how we do it? So like it becomes, there's opening, and now we expand it by using opening there. Okay, so not worry. So here again we can use closing bracket here, so don't worry. So now if we have to say for this condition, so if we expand it by using the opening bracket. Okay, so it is still valid. And now here for this condition we can't use closing bracket. Because there's a close become greater than opening, so it become invalid. So this is not possible. So I think you are now understandable how we expand our this string till the size of 2n. Like we have the two operations here. So how we have two operation? First of all, what is the case one? If we have to first of all, since we initialize our open is from 0 and close is from 0, and how we reach it? So we reach it from till open becomes the n, and close till become n. Okay, so like what is the case one? So case one is, if our open is less than n, use open simply. Okay, what is the case 2? If close is less than n, and close is less than, we don't have to bother about this condition for close less than n, because open is greater than n means close is, since there are some is n. So for this we can use the close here. So simply we use this bracket. So like for the starting we check whichever the condition is follow, case 1 or case 2. Since close is equal to open means we have to use case 1. Okay, now here case 1 case 2, here now either case 1 case 2. So simply we only have the two cases, and like expanding our this string till the size 2n using these two cases. Okay, so this is my optimal way. So like simply again I explain in the my brute force, I simply initialize my vector of a string there, I initialize my string there, I two variables there, open and close there, and I simply pass them in my solve function. And now how to write this solve function? So there's the s path, the answer, and open and close. So this is my base condition. If my s size is become 2n, so it is like in the brute force, like I say I have to check for the 2n it is valid or not, but there's no need to check, because we like check at each step. If it become invalid, so we don't expand this in this further recursive tree. So if it reach to 2n, it's surely that it is valid here. So we simply put it in our answer. Okay, now the what is the two cases? If our open is less than, what like either our open is less than, either our close is less than, or either our open is equal to close. Okay, so now if I'm talking about open is less than, we simply insert open bracket and solve for this. And like after like it is also necessary that if we have to push, there's a need for the pop back. Okay, simply what is the case 2 that I'm saying about this? So if it is close is less than open, we simply insert the open close bracket there and solve for this. And so we don't have to worry about this, we simply calling the solve function, so it can do for the further operations. So if our size become 2n means it is surely that it need to be valid there. And so we return finally we return our answer there. So what is the simply first of all, we space complexity is again of 2n there. And what is the time complexity here? So since here again we have use of 2 power n, and there's not of extra 2n here. Why there's not 2n extra there? Because we don't usually check at the final condition whether it is valid or not, because we check at every place there. So there's a simply of 2 power n, there's a time complexity, and of 2n is simply the space complexity for this. Thank you for